You have one on your fridge right now, holding up a photograph or a grocery list. A small magnet strong enough to grip steel through a sheet of paper, weak enough that you can pull it free with 2 fingers. Out in the galaxy, there is a magnet so strong that it would wipe the card in your wallet from halfway to the moon and pull the atoms in your hand apart long before you ever drew near it. That object is a kind of dead star called a Magnetar, and it carries the strongest magnetic field we have ever found anywhere in the universe. Over the next couple of hours, we'll build up to it slowly, one simple step at a time, starting from that fridge magnet and ending at a place where matter itself stops behaving. If you like taking your time with a big idea, take a moment to subscribe, and we will begin. The question is an easy one. How strong can a magnet get? Pick up the magnet on your fridge, feel it grip the steel through a sheet of paper, then pull it free with 2 fingers. That small click of force is something you have known your whole life. It is also one of the 4 basic forces that hold the universe together, the same force that turns a compass needle toward the north and carries every radio signal through the air. The magnet in your hand is a quiet, tamed version of it. A fridge magnet is weak as magnets go. Its pull measures about 100 gauss. Gauss is just the unit we use to size up a magnetic field, the way we use degrees to size up heat. The Earth itself, the whole spinning planet under your feet, makes a field of only about half a gauss at the surface. That is why a compass needle moves so gently. It is answering a faint pull spread across the entire world. You can climb this ladder of strength step by step. A strong magnet on a workbench might reach a few hundred gauss. The big machines that let doctors see inside your body, the MRI scanners, run near 15,000 to 30,000 gauss. Stand near one and it will tug the keys from your pocket and stop a watch. Those are among the strongest steady magnets we build on Earth, and they take huge coils, cold metal, and a great deal of power to hold. Now hold that number in your mind. 30,000 gauss, the strongest field most people will ever stand near, made by a machine the size of a small room. Out in the galaxy, there are objects whose fields are not 30,000 gauss, and not 1,000,000, but 1,000 trillion. Written plainly, that is a 1 with 15 zeros after it. It is a number so far past the fridge magnet that the words start to lose their grip, which is exactly the problem we're going to solve over the next couple of hours. We will build a sense of scale you can actually feel. The object that carries that field is a dead star. It is small, only about the size of a city, and it is made of the densest matter that exists outside of a black hole. We call it a magnetar. The name simply joins the word magnet to the word star, and it means what it sounds like, a star that is mostly magnet. A magnetar's field is so strong that it does not just move metal, it reorders matter itself. It would wipe the strip on every card in your wallet from halfway to the moon. Come closer, and it would reach into the atoms of your body and stretch them, because at that strength, a magnetic field stops being something that acts on objects and starts being something that rewrites them. Nothing we know of survives close to 1. That gap between the gentle click on your fridge and a force that pulls atoms out of shape is the whole story. It is a real object, sitting in our own galaxy right now, and everything about it follows from physics we can trace, step by step, starting from things you already hold in your hand. So we begin at the bottom of the ladder with the magnet on the fridge, and we will not skip a rung. To understand how a magnet gets that strong, we first have to understand the kind of object that carries it, and that object is born in the death of a giant star, in one of the most violent events the universe ever stages. Before we can reach the magnet, we have to watch a star die. Every star is a war between 2 forces that never stops, not for a single second, across millions or billions of years. On one side is gravity, pulling every part of the star inward, trying to crush it down to a point. On the other side is the heat and pressure of the star's core pushing outward, trying to blow it apart. A star lives in the narrow balance between the two. The sun has held that balance for about 4.5 billion years, and it will hold it for billions more. The outward push comes from fusion. Deep in the core, where the temperature reaches millions of degrees, hydrogen atoms are slammed together so hard that they stick, fusing into helium. Each time they join, a little mass turns into a great deal of energy. The relation Albert Einstein wrote as energy equals mass times the speed of light squared. That energy floods outward as light and heat, and its pressure holds the star up against its own weight. Fusion is the fire that keeps the star standing. A star like the Sun burns hydrogen calmly for a very long time. But the giants, the stars 8 times the mass of the Sun and more, burn fierce and fast. The more massive a star is, the harder gravity squeezes its core, the hotter the core runs, and the quicker it tears through its fuel. A star 20 times the Sun's mass may live only a few million years, a brief, bright life against the long patience of the Sun. When the hydrogen in the core runs low, the star does not simply go out. The core contracts, heats further, and starts to fuse helium into carbon. When the helium runs low, it fuses carbon. A massive star works its way up the ladder of elements, each stage shorter and hotter than the last, burning carbon, then neon, then oxygen, then silicon. Picture an onion with shell inside shell, each layer fusing a heavier element than the one outside it, all of them feeding heat to hold the star up. Every step buys less time. Hydrogen might last millions of years. The later stages pass in centuries, then years, then days. The silicon burning stage, the last one, can last only a single day. The star is racing now, climbing the ladder faster and faster, and it is running toward a wall. The wall is iron. When fusion builds up to iron in the core, the climb stops. Up to iron, fusing atoms together releases energy and feeds the outward push. But iron is the most tightly bound nucleus there is. Fusing iron does not release energy. It costs energy. The moment the core becomes iron, the fire that held the star up has nothing left to burn. The fusion that fought gravity for millions of years simply ends. For a heartbeat, the iron core sits there, about the size of the Earth but far heavier, holding itself up on the last of its pressure. It is supported now not by fusion but by the stubbornness of its own packed particles, a quantum effect we will meet again. Gravity has not stopped pulling for one instant. It has only been waiting. And the core keeps growing, because the shells around it keep dumping fresh iron onto it. There is a limit to how much weight that quantum stubbornness can hold, a mass first worked out by Subrahmanyan Chandrasekhar, about 1 4/10 times the mass of the Sun. The instant the iron core crosses that line, it can no longer hold itself up at all. What happens next happens in less than a second. The star is about to fall in on itself. The iron core has crossed its limit, and now gravity wins all at once. The collapse begins. The core, a ball of iron about the size of the Earth, falls inward on itself, and it falls fast. The inner part caves in at speeds reaching 70,000 kilometers a second, nearly a quarter of the speed of light. Something the size of a planet collapses in about the time it takes to read this sentence. As the core falls, it heats and crushes, and the matter inside it changes. The pressure becomes so extreme that protons and electrons are forced together. They merge. A proton and an electron pressed hard enough combine into a neutron, and a tiny ghostly particle called a neutrino flies free. Across the whole core this happens at once, turning ordinary matter into a packed ball of neutrons, and releasing a flood of neutrinos so vast it is almost beyond counting. The core keeps falling until it cannot fall any further. The neutrons are now packed so tightly that they push back with tremendous force, the same quantum stubbornness as before but far stronger, because 2 neutrons refuse to share the same state. The collapse slams into this wall and stops hard in a fraction of a second. The center has reached the density of an atomic nucleus, and it can compress no more. When the falling core hits that wall, it bounces. A shock wave tears back outward through the still in falling layers of the star. By itself that shock would stall, but the flood of neutrinos pouring out of the new core dumps energy into the gas behind it. and the shock is reborn and driven outward through the body of the star. It races up through the layers, the silicon, the oxygen, the carbon, the helium, the hydrogen, and blows them off into space. This is a supernova. For a few weeks, a single dying star can shine as bright as 100 billion ordinary stars, as bright as a whole galaxy. The light of it can cross the universe. People have looked up and seen these without knowing what they were. The Crab Nebula, that beautiful tangle of glowing gas, is the wreckage of a star that Chinese and other astronomers recorded exploding in the year 1054, bright enough to be seen in daylight for weeks. Walter Baird and Fritz Zwicky, two astronomers working in California in the 1930s, were the ones who gave this event its name. They coined the word supernova for it, to mark it apart from the lesser flare-up stars sometimes show, and they guessed, correctly, that the explosion was only the announcement. The real event was at the centre, because the supernova is not the death of the star. It is the birth cry. The outer layers are thrown away, scattered across light years, seeding space with the heavy elements the star made, the oxygen you breathe and the iron in your blood. But the core that bounced and held does not go anywhere. It stays behind at the centre of the spreading wreck. What remains is a single object, the crushed and ringing core, made almost entirely of neutrons. It holds more than the mass of the Sun, and it is now unimaginably small. The fusion fire is gone and it will never burn again, but the object left behind is far stranger than the star that made it. It is a neutron star. A spoonful of it would weigh more than a mountain, and to believe that we need to look at it closely. So let us hold the new object in our hands carefully and see what kind of matter it is made of. Take the Sun, a ball of glowing gas wide enough to swallow 1,000,000 Earths, and imagine squeezing it down. Squeeze until it is no longer the width of 1,000,000 Earths, no longer the width of one. Squeeze until the whole thing, more mass than the Sun, fits inside a city. That is a neutron star. It holds about 1.5 times the mass of the Sun inside a ball roughly 20 kilometers across, small enough to sit inside the ring road of a town. The number that matters here is density, which simply means how much mass is packed into a given space. A neutron star is the densest material that exists short of a black hole. To picture its density, think of a single teaspoon. A level teaspoon of ordinary water weighs about 5 grams. A level teaspoon of neutron star material would weigh about 1 billion tons. One small spoon would outweigh every car, ship and building in a large city, all at once. That is hard to believe, so it is worth understanding why it is true. Ordinary matter is mostly empty space. An atom is a tiny dense nucleus with a cloud of electrons whirling far out around it, and between the nucleus and that cloud there is nothing at all. If an atom were the size of a sports stadium, the nucleus would be a single pea at the centre, and the rest would be air. The solid table you knock on is almost entirely empty, held apart by those electron clouds. In a neutron star, that empty space is gone. The collapse we just watched crushed the electrons into the protons, turned them into neutrons, and packed those neutrons together until they touched. There are no more atoms, no more electron clouds keeping things apart. There is just one continuous mass of neutrons, pressed close at the same density as the inside of an atomic nucleus. A neutron star is, in a real sense, a single enormous nucleus, the size of a city. The gravity at its surface follows from all that mass in so small a space. It is staggering. The pull at the surface of a neutron star is around 100 billion times the gravity you feel standing on the Earth. A marshmallow dropped onto the surface would arrive with the energy of an atomic bomb. Nothing could stand there. Nothing could even fall there and remain itself. The surface, if you could somehow look at it, would be smooth, almost beyond meaning. The whole star's gravity is so strong that no bump can rise more than a few millimeters before being pulled flat. The tallest mountain on a neutron star might be the height of a sheet of paper. It is a near-perfect sphere of the strangest matter in the universe, and it is hot, born at temperatures around 1 trillion degrees, cooling over thousands of years but staying searingly hot by any human measure. It spins, often very fast for reasons we will come to, and it carries a magnetic field because all of this, the spin and the field, was inherited and concentrated from the giant star that died. This is the object at the heart of our story. A magnetar is a neutron star, with everything a neutron star already is, all of that density and gravity and strangeness, and then one feature pushed to an extreme. The neutron star is the canvas. The magnetic field is what gets painted on it. The remarkable part is that people knew this object should exist before anyone ever saw one. The idea came first, worked out on paper from the bare facts of physics. Let us go back to the year the neutron itself was found. In 1932, a physicist named James Chadwick, working in Cambridge, found the neutron. People already knew the atom had a nucleus, and that the nucleus held positively charged protons. But the masses did not add up. There seemed to be extra weight in the nucleus that carried no charge. Chadwick ran the experiments that pinned it down. A particle about as heavy as a proton but electrically neutral. He called it the neutron. It completed the basic picture of what an atom is built from. That discovery landed in 1932. Just 2 years later, in 1934, two astronomers took that brand new particle and made a leap that still seems bold today. Walter Baade and Fritz Zwicky, working at Mount Wilson and Caltech in California, were studying the bright stellar explosions they had named supernovae. They were trying to understand where all that energy came from. Their answer was a single, startling claim in a short scientific paper. They proposed that a supernova marks the transition of an ordinary star into a new kind of star made of neutrons. The energy of the explosion, they reasoned, came from the collapse of the star's core into an incredibly dense small body packed with these newly discovered neutrons. They wrote, in plain terms, that a neutron star would be the leftover heart of the blast. Think about how little they had to go on. The neutron was 2 years old. No one had any direct evidence such a star existed. There was no instrument that could have seen one. Baade and Zwicky reasoned their way to it from the physics alone, from what must happen when a massive core collapses and matter is crushed past the point where atoms can survive. They saw the answer before the universe showed it to them. The two men made an odd pair. Fritz Zwicky was brilliant, combative, and famously blunt, a Swiss-trained physicist who feuded with colleagues and trusted his own judgment over almost anyone's. Walter Baade was careful, patient, a meticulous observer of the sky. Together they reached further than either might have alone, and several of their ideas, dismissed or ignored at the time, turned out to be right decades later. Zwicky also reasoned his way to unseen mass in galaxies, what we now call dark matter, long before the field caught up to him, but the neutron star idea sat quiet for a long time. The trouble was simple. Such a star would be tiny, only a few kilometers across, and not very bright in ordinary light. The galaxy is full of stars that shine. A neutron star is a faint small ember by comparison. Through the telescopes of the 1930s, 40s and 50s, there was no way to pick one out. The prediction was on the table, but no one could test it. For more than 30 years it stayed that way, a clever idea waiting for the sky to confirm it. Some physicists worked out the theory further. Robert Oppenheimer, before the war that made his name, calculated with a colleague how such a star would hold itself up and how much it could weigh. Lev Landau, the great Soviet physicist, had thought along similar lines. The math grew sturdier, but the object itself stayed hidden, unseen, possibly imaginary. It would take a completely different kind of telescope to find one, and a young graduate student paying close attention to a strange, regular signal that everyone else might have brushed aside. The neutron star would announce itself not as a faint dot of light, but as a beat, ticking with a steadiness that nothing in the heavens was supposed to have. When it finally came, the signal was so precise that the people who found it briefly wondered whether it was natural at all. That discovery, in 1967, is where the story turns from prediction to proof. In 1967, a young graduate student named Jocelyn Bell was watching a radio telescope do its work in a field outside Cambridge. in England. The telescope was not a single dish. It was a sprawling array of wires and posts she had helped build by hand, covering several acres, designed by her supervisor Anthony Hewish to study distant radio sources. It recorded what it saw as ink lines on rolls of paper, meters and meters of it, which Bell read by eye. One day she noticed something she later described as a bit of scruff on the chart, a small ragged mark that did not look like the usual sources and did not look like ordinary interference either. It was easy to ignore. She did not ignore it. She had built the instrument and she knew its habits, and this was not one of them. She went back and looked at it more closely, and she found that the scruff returned, always from the same patch of sky. When she managed to record it at higher speed, the signal resolved into something astonishing. It was a series of sharp pulses, each one a brief blip of radio energy, repeating with extraordinary regularity. The gap between pulses was about 1 1/3 seconds, and it held at beats so precisely you could have set a clock by it. Nothing in nature was known to keep time like that. The pulses were as steady as a machine. That steadiness raised an unsettling thought, a signal that regular, that artificial seeming, might be a beacon. Half in seriousness, the team labelled the source LGM-1 for Little Green Men, allowing the faint possibility that they had stumbled onto a signal from another civilization. Bell, working late and a little unnerved, was not eager for that explanation. Then she found a second pulsing source in a different part of the sky, beating at a different rate. 2 separate civilizations signalling Earth at once was far too much to swallow. These had to be natural objects. The beat itself was the key to what they must be. For something to flash every second or so, it had to be small. A large object cannot turn on and off that quickly, because its own size blurs any rapid signal. To pulse once a second, the source had to be only thousands of kilometers across at most, perhaps far less. And to repeat so steadily, it almost certainly had to be spinning, sweeping a beam past the Earth the way a lighthouse sweeps its light past a ship. A small, dense, fast-spinning object sweeping a beam of radio waves. The pieces fit one thing, the neutron star that Barden's wiki had predicted 33 years earlier. Here at last was the evidence. A neutron star spinning rapidly, with a magnetic field that funnels radio energy out of its poles in 2 tight beams, would appear to pulse each time a beam crossed our line of sight. The team called these objects pulsars, short for pulsing stars. The discovery was historic, and the Nobel Prize that followed in 1974 went to Anthony Hewish for the work, alongside another radio astronomer. Jocelyn Bell, the person who actually spotted the scruff and chased it down, was not included, a decision that many in the field have argued about ever since. Bell herself responded with remarkable grace over the years, and went on to a long and honoured career. Decades later, she was awarded a major physics prize and gave the entire sum, several $1 million, to support students from underrepresented backgrounds. The pulsar proved the neutron star was real. It also handed us a puzzle. An object that spins a full turn in just over a second, or in some cases hundreds of times a second, is doing something that needs explaining. The answer is hiding in the collapse we already watched. The same fall that made the star also wound it up. You have seen a figure skater do this, even if only on a screen. She spins on the ice with her arms stretched wide, turning at a steady, graceful pace. Then she pulls her arms in tight against her body, and without any push, without any effort, she speeds up. She spins faster and faster, a blur, until she throws her arms back out and slows again. She did not add any force, she only changed her shape. This is one of the deep rules of physics, called the conservation of angular momentum. Spin, once a thing has it, does not simply vanish, it is conserved. If a spinning object pulls its mass inward, closer to the centre, it must spin faster to keep its total spin the same. The skater pulling in her arms and a collapsing star are the same physics, only the star takes it to an extreme no skater could survive. Every star spins, slowly, lazily. The Sun turns once about every 25 days at its equator, a stately rotation you would never notice by looking. The Sun is enormous, well over 1 million kilometers across, so even that slow turn means its surface is moving at a fair clip. All of that spin, that angular momentum is stored in the giant slow body. Now collapse the core of such a star. Take the central region, hundreds of thousands of kilometers across, and crush it down to a ball only 20 kilometers wide. That is the skater pulling her arms in, but pulling them in by a factor of tens of thousands. The spin has nowhere to go. It is conserved, so as the core shrinks, it must turn faster and faster to hold the same total amount. The result is breathtaking. A core that was turning once a month, squeezed down to the size of a city, can end up spinning many times every second. The young pulsar at the center of the Crab Nebula, the wreck of that star seen exploding in 1054, spins about 30 times a second. 30 full turns every second of an object heavier than the Sun. The fastest neutron stars known, spun up by other means, turn over 700 times a second, their surfaces moving at a sizable fraction of the speed of light. Hold that picture. A ball of city size and more than solar mass, whirling hundreds of times a second, so fast and so heavy that it bulges slightly at its equator and keeps near perfect time. This is why Jocelyn Bell's signal beats so steadily. A spinning body that massive is an almost flawless clock. It has too much momentum to be easily disturbed, so each turn comes right on schedule year after year. Some pulsars keep better time than the best atomic clocks on Earth, at least over short stretches. The same conservation rule that speeds up the spin also does something to the star's magnetic field. And this is the thread we have been following all along. When you crush the star down, you crush its magnetism with it. The field lines that were spread across a vast star get squeezed into that tiny ball, and a squeezed field is a stronger field. The spin gets concentrated, and so does the magnet. That is the bridge we need. We have a small, dense, blazingly fast object, keeping time like a clock. Now we ask where its magnetism comes from, and how strong it gets in an ordinary neutron star, before we ever reach the extreme case. Every neutron star is magnetic. The magnetar is only what happens when that magnetism is pushed 1,000 times further than usual. To see how far that is, we first have to set the ordinary level. Magnetism, at its root, comes from moving electric charge. A current flowing through a wire makes a magnetic field around it. The Earth's field comes from molten metal churning in its core. The Sun's field comes from the motion of its hot charged gas. Wherever charged matter moves in bulk, magnetism follows. A star is a vast ball of charged moving matter, so every star carries a magnetic field of its own. The Sun's field is modest in most places, around 1 to a few gauss across its surface, close to what your fridge magnet makes, though in sunspots it can climb to thousands of gauss. Spread across the whole enormous body of the Sun, though, that field holds a great deal of total magnetism. The field threads through the entire star, in and out of its surface, looping through space. It is woven into the star. Now think back to the collapse. When the core of a massive star falls inward and shrinks down to the size of a city, the magnetic field does not get left behind. It is locked into the charged matter, frozen into it, and it falls inward with everything else. As the core shrinks, the field lines that were spread across a wide region get crowded into a tiny one. Crowding the field lines together makes the field stronger, in proportion to how much the area shrinks. There is a clean way to picture this. Imagine the magnetic field as a set of lines passing through the surface of the star, like threads stuck through a balloon. The number of threads stays the same, but as the balloon shrinks, those same threads pass through a much smaller area, so they are packed far more tightly. The field strength is just how tightly those lines are packed. Shrink the star by some factor in radius, and the field grows by that factor squared. The numbers work out to something powerful. A star's core might start with a field of 100 gauss or so. Crush it from the width of a star down to 20 kilometers, and the field can be amplified by a factor of around 1 billion. The ordinary neutron star ends up with a magnetic field near 1 trillion gauss. Written out, that is a 1 with 12 zeros, 1 million gauss. 1 trillion gauss is already a field beyond anything on Earth. It is 100 million times stronger than the most powerful MRI scanner, a field so strong it would be lethal far from the star's surface. This is the normal level, the field that almost every pulsar carries, the field that funnels Jocelyn Bell's radio beams out of the magnetic poles. When we talk about pulsars sweeping their lighthouse beams across the sky, this 1 trillion gauss field is the engine doing the sweeping, so the ordinary neutron star is already one of the most strongly magnetized objects we know. The collapse alone, the simple crushing of the field, gets you to 1 trillion gauss without any special trick. For decades, that seemed to be the whole story. Neutron stars were strongly magnetic, all in the same broad range, and the differences among them seemed small. But 1 trillion gauss is not where this ends. A Magnetar's field is not 1 trillion gauss. It is around 1,000 trillion gauss, 1,000 times stronger than the strongest field the simple collapse can explain. Crushing the old field is not enough to reach it. Something else has to happen in the first moments after the star is born. Some engine that takes the inherited field and multiplies it again, 1,000-fold. To find that engine, we have to follow the trail of evidence the way astronomers actually did. And the trail begins with a single, strange burst of gamma rays that arrived at the Earth on a day in March in 1979 from a star that did not behave like any pulsar known. On the 5th of March, 1979, a wave of gamma rays swept through the solar system. Gamma rays are the most energetic form of light, far beyond visible light or even X-rays, the kind of radiation that comes from the most violent events in nature. This particular wave was detected by a fleet of spacecraft scattered across the planets, including 2 Soviet probes named Venera that were on their way past Venus, and instruments near the Earth, the Moon, and beyond. Because the wave hit different spacecraft at slightly different times, scientists could triangulate where it came from, the same way you might locate a sound by how long it takes to reach 2 ears. The signal pointed back to a specific spot, a tattered cloud of gas called N49, sitting not in our own galaxy but in the Large Magellanic Cloud, a small companion galaxy about 160,000 light-years away. That cloud was the wreckage of an old supernova. The burst was extraordinary in 2 ways. First, its sheer power. In the first fraction of a second, it was brighter in gamma rays than anything ever recorded from beyond our galaxy. A spike of energy so sharp it overwhelmed the detectors. Had it gone off nearby, it would have been catastrophic. From across the distance to another galaxy, it still slammed the instruments to their limits. Second, and stranger, after that first violent spike, the signal settled into a softer glow that faded over a few minutes, and as it faded, it pulsed. It flickered with a steady beat, once every 8 seconds. That 8-second rhythm was the fingerprint of a spinning neutron star, an object turning once every 8 seconds and sweeping its emission past the Earth. So the source was a neutron star, but neutron stars were not supposed to do this. A spin of 8 seconds is slow for a neutron star, and the burst of gamma rays was something pulsars simply did not produce. Ordinary pulsars hum along steadily, beaming radio waves, not erupting in colossal flashes of gamma rays. This object had done both, a slow spin and a violent gamma ray outburst. It did not fit the established picture of what a neutron star was. Then it did something that ruled out most other explanations. It burst again. Over the following years, from that same patch of sky, more flashes of gamma rays arrived, softer than the first great spike, but clearly from the same source. Whatever this was, it repeated. A single catastrophe, like 2 stars colliding, can only happen once. This thing erupted over and over from the same point. astronomers gave this new class of object a careful, descriptive name. They called them soft gamma repeaters. Soft because the gamma rays were at the lower, less energetic end of the gamma range, gentler than the hardest gamma ray bursts. Repeaters because they fired again and again. The name made no claim about what the objects were. It only described what they did, which was honest, because nobody yet knew what they were. Here was a deepening mystery. Something was sitting in the wreck of an old supernova, spinning slowly, and every so often releasing bursts of gamma rays with a power that strained the imagination. That energy had to come from somewhere, and an ordinary neutron star, even a strongly magnetized one, had no obvious way to supply it, and the soft gamma repeaters were not the only strange neutron stars turning up. Around the same time, astronomers using X-ray telescopes were finding a second odd family, neutron stars that glowed in X-rays far more brightly than their slow spin could explain. For a while, these two groups of misfits were studied separately, each with its own name and its own puzzle. The clue that would join them was the strength of their magnetism, though no one had measured it yet. By the late 1980s and into the 1990s, astronomers were tracking two separate families of strange neutron stars, and for a long while no one realized they were looking at the same thing twice. The two families had different names, were found by different methods, and were studied by different groups of people. Each was a puzzle on its own. Together they were a puzzle squared. The first family we have already met, the soft gamma repeaters. These were the objects that fired off bursts of low-energy gamma rays, again and again from the same point in the sky. The March 1979 event had announced the first one. Over the years, a small handful more were found, each a slowly spinning neutron star prone to sudden, powerful gamma-ray outbursts that no ordinary pulsar could match. The second family was found in X-rays, and was given the name anomalous X-ray pulsars. The word anomalous simply means out of the ordinary, and that is exactly what these were. They were neutron stars that pulse steadily in X-rays, like many neutron stars do, but they broke a basic rule. Most X-ray bright neutron stars get their energy by pulling gas off a companion star, a partner orbiting close enough to feed them. These pulsars had no companion. They were alone, yet they shone in X-rays far more brightly than their slow rotation could account for. So here were the two puzzles side by side. The soft gamma repeaters release sudden bursts of gamma rays with no clear power source. The anomalous X-ray pulsars gave off a steady glow of X-rays with no clear power source. Both were slowly spinning neutron stars, with spin periods in the range of a few seconds to a dozen seconds. Both were alone, with no companion star to feed them. Both were producing far more energy than their spin could supply. The shared traits were piling up, but the two communities had grown up apart. The gamma-ray astronomers and the X-ray astronomers worked with different instruments and described their objects in different language. It is one of the quiet truths of science that the same thing can hide behind two names for years, simply because the people who study one half rarely sit in the same room as the people who study the other. Look at the list of shared traits, though, and a single picture begins to form. Slow spin, no companion, excess energy that rotation cannot explain. If there were one kind of object that could produce all of this, it would have to carry a reservoir of energy that an ordinary neutron star did not. It would need a power source built into the star itself, something that did not depend on spin and did not depend on a partner. There is really only one place that much spare energy could be stored inside a lone neutron star, not in its rotation, which was slow, not in any companion, which did not exist. The energy had to be stored in the one thing left, the magnetic field. If the field were not a trillion gauss, the ordinary level but 1,000 times stronger, then the field itself would hold a colossal reserve of energy, enough to power both the steady X-ray glow and the sudden gamma-ray bursts. That was the leap. A neutron star so magnetized that the field, not the spin, ran the show. A star where the magnetism was the dominant force, the source of the light, the cause of the bursts, the engine of everything strange about it, The soft gamma repeaters and the anomalous X-ray pulsars would then be the same kind of object, seen in two moods, one prone to outbursts and one glowing steadily, both powered by a field beyond anything yet imagined. Two physicists put that idea on paper in 1992, and they gave the object a name that has stuck ever since. In 1992, two physicists, Robert Duncan and Christopher Thompson, published the idea that pulled all of these threads together. They were working on a hard question. When a neutron star is born in the first seconds of its life, how strong can its magnetic field actually become? Most people assume the answer was the familiar trillion gauss, the level you get from simply crushing the old star's field. Duncan and Thompson found a reason to think it could go far higher. Their proposal was a new class of neutron star, one in which the magnetic field reached 1,000 trillion gauss or more, 1,000 times the ordinary level. At that strength, the field would no longer be a side feature of the star. It would be the most important thing about it, the dominant force shaping how the star behaves, stores energy, and dies. They coined a name for this kind of object by joining two words. Magnetic star became Magnetar. The name was more than a label. It carried a claim about what runs the object. A pulsar is named for its pulse, the beam it sweeps. A magnetar is named for its magnetism, because in this kind of star the magnetic field holds more energy than the spin, and that field is the engine behind everything the star does. The bursts, the glow, the slow changes, all of it would be driven by the field winding down and rearranging itself. Duncan and Thompson worked out what such a field would imply, and the implications were severe. A field of 1,000 trillion gauss stores an immense amount of energy, far more than the star's rotation. That reservoir, slowly leaking and occasionally snapping into a new arrangement, could power the steady X-ray glow of the anomalous X-ray pulsars. And a sudden, violent rearrangement of the field could release a burst of gamma rays, exactly like the soft gamma repeaters produced. One idea explained both families at once. It also explained the slow spin, a field that strong acts like a powerful brake. As the star spins, its giant magnetic field drags against the thin gas and radiation around it, bleeding away rotational energy and slowing the spin. A magnetar would spin down fast, reaching the sluggish few-second periods of the soft gamma repeaters and the anomalous X-ray pulsars in just a few thousand years. The slow spin was not a problem to be explained away. It was a prediction of the model. The proposal was elegant, but at first it was only a proposal. A beautiful idea is not the same as a confirmed fact, and the Magnetar model made a bold claim that fields 1,000 times stronger than anyone had measured were real and sitting in our galaxy. Many scientists were intrigued. Many were skeptical. The idea needed a test, some measurement that could show, directly, that these objects really carried a field of 1,000 trillion gauss, and not the ordinary trillion. There was, in principle, a way to check. If a magnetar's enormous field really was breaking its spin, then the star should be slowing down, and slowing down at a measurable rate. The stronger the field, the faster the slowdown. Measure how quickly one of these objects is losing its spin, and you can work backward to the strength of the field doing the braking. The field itself is invisible, but its grip on the spin is not. That measurement was difficult. It meant timing the pulses of one of these stars precisely enough to catch the tiny, steady lengthening of its spin period over months and years. But it was possible, and within a few years it was done. Before we reach that test, we should understand the engine Duncan and Thompson proposed, the process that could take an ordinary inherited field and multiply it 1,000-fold in the first moments of a star's life. We left an open question 2 chapters ago. Crushing the old star's field gets you to 1 trillion gauss, the ordinary level. A magnetar's field is 1,000 times stronger than that. Crushing alone cannot explain it. Something has to take the inherited field and amplify it again by a factor of 1,000 in the brief window after the star is born. Duncan and Thompson's answer was a process called a dynamo. A dynamo is simply a way of turning motion into magnetism. The principle is the same one behind the generator in a power plant or the alternator in a car. When you churn charged matter in the right way, you generate electric currents, and those currents make their own magnetic field, which can feed back and grow. The Earth runs a dynamo in its molten core. The Sun runs one in its churning gas. A dynamo converts the energy of movement into the energy of a magnetic field. Now picture a neutron star in the first seconds of its life, just after the collapse. It is not the calm, settled object it will become. It is a roiling, boiling sphere, blisteringly hot, around 1 trillion degrees, with its material churning violently from the inside out. Heat is pouring out of it, and that heat drives convection, great currents of neutron-rich matter rising and sinking, much as hot water churns in a boiling pot. The newborn star is in furious motion within. The other ingredient is spin, and here is the crucial point. If the newborn neutron star is spinning slowly, the convection churns but does not organize, and you get only the ordinary field. But if the newborn star is spinning extremely fast, turning once every few thousandths of a second, then the spin and the churning convection lock together into an efficient dynamo. The fast rotation organizes the chaotic motion into a powerful coordinated engine that builds the magnetic field up and up. Duncan and Thompson found that there is a threshold. If the newborn neutron star spins fast enough, with a period shorter than roughly 10 milliseconds, the dynamo runs at full strength and can amplify the field to 1,000 trillion gauss, the Magnetar range. If it spins slower, the dynamo is feeble, and you get an ordinary pulsar with its ordinary trillion gauss field. The difference between a normal neutron star and a magnetar might come down to how fast the core was spinning in the first instant it formed. This makes magnetars relatively rare, which fits what we see. Only a small fraction of newborn neutron stars are likely to spin fast enough to run the dynamo at full power. Most are born spinning more sedately and grow up as ordinary pulsars. A magnetar would be the child of a particularly fast-spinning core, a rarer birth, which is one reason these objects are uncommon in the catalogue. The dynamo runs for only a short time, maybe the first 10 seconds or so of the star's life, while it is still hot and churning and spinning fast. After that, the convection dies down, the star settles, and the field it has built is frozen into the rigid body of the neutron star, locked in place. The engine shuts off, but the magnetism it forged remains, 1,000 trillion gauss held in a ball the size of a city for thousands of years to come. So the picture is complete in theory. A fast-spinning newborn neutron star runs a dynamo for a few seconds, amplifies its field 1,000-fold, then freezes that monstrous field into place. It is an elegant story, but it was, in 1992, still only a story. The field is invisible. You cannot photograph 1,000 trillion gauss. To know whether any of this was real, someone had to find a way to measure the strength of a magnetar's field from across the galaxy, and that is exactly what happened next. The test came in 1998, and it was led by an astronomer named Chryssa Kouveliotou, working with NASA and a team of colleagues. They turned their attention to one of the soft gamma repeaters, an object catalogued as SGR 1806-20 sitting in our own galaxy. Their plan was straightforward in idea and demanding in practice. They would measure how fast this star was spinning, and then measure how fast that spin was slowing down. Recall the logic. A magnetar should carry a field so strong that it acts as a fierce brake on the star's rotation. The field drags against the surroundings and bleeds spin away. The stronger the field, the harder the braking, and the faster the star slows. So if you can measure the spin and the slowdown, you can calculate the field strength doing the braking without ever seeing the field directly. The slowdown is the field signature, written in the timing of the pulses. Kouvelioutou's team used an X-ray telescope in orbit, the Rossi X-ray Timing Explorer, an instrument built precisely for catching rapid changes in X-ray sources. They watched the star carefully over time. They found it was spinning once every 7.5 seconds, the slow rotation typical of these objects. Then they watched longer and measured the crucial number, the rate at which that 7.5 second period was getting longer. The star was slowing down, and it was slowing down quickly. Each rotation was taking a tiny bit longer than the last, and the rate of that lengthening was large. When the team put the spin and the slowdown into the equation that relates them to magnetic field strength, the answer came out near 1,000 trillion gauss. There it was. Not a calculation from theory, but a measurement, drawn from the timing of a real star, landing squarely in the range Duncan and Thompson had predicted 6 years before. This was the moment the Magnetar went from idea to established fact. The field strength predicted by the theory was now confirmed by observation, measured in the slowing spin of an actual object in our galaxy. The soft gamma repeaters really did carry fields 1,000 times stronger than ordinary pulsars. The thing that had seemed almost too extreme to believe was simply there, in the sky, doing exactly what the theory said it should. With the field strength confirmed, the rest of the picture clicked into place. The same kind of measurement tied the soft gamma repeaters firmly to the Magnetar model, and soon the anomalous X-ray pulsars were folded in as well, shown to carry similar enormous fields. The two families of misfit stars were finally understood as one. They were Magnetars, in different states, all of them powered by fields near or above 1,000 trillion gauss. The confirmation also let astronomers read the life story of these stars. A Magnetar's powerful field breaks it so hard that it slows from a rapid newborn spin to a sluggish few-second rotation within a few thousand years. The same breaking means the active bursting phase of a Magnetar's life is brief. After 10,000 years or so, the field has wound down enough that the star quiets, no longer flaring, fading toward the great population of silent dead neutron stars that fill the galaxy. So by the end of the 1990s, the Magnetar was real, measured, and understood in outline. We knew how it formed, why it spun slowly, where its energy came from, and roughly how long it lived. What remained was to truly grasp the field itself, this 1,000 trillion gauss we keep naming. The number is easy to say and almost impossible to feel. Before we can understand why nothing survives near a Magnetar, we have to build a real sense of how strong that field actually is. We keep saying 1,000 trillion gauss, and the words slide past without landing. The human mind is not built to feel a number that large, so let us build a ladder, rung by rung, starting from something you can touch and climbing all the way up, so that by the top you have a real sense of the height. Start at the bottom. The Earth's magnetic field, the one that turns a compass, measures about half a gauss at the surface. That is the field you live inside every day, far too weak to feel, strong enough only to nudge a floating needle toward the north. Call that the ground floor, 1/2 of 1 gauss. Step up to the magnet on your fridge. It runs around 100 gauss, a couple hundred times the Earth's field. You can feel this one. It grips steel and holds a photograph. From the Earth's gentle nudge to the fridge magnet's firm little clasp is already a jump of a few hundredfold, and you have only taken one step. Now climb to the strongest magnet most people will ever stand near, the MRI scanner in a hospital. A typical one runs near 15,000 to 30,000 gauss. That is strong enough to yank a steel oxygen tank across a room, strong enough that the machines come with serious warnings. Call it 30,000 gauss, a few hundred times stronger again than the fridge magnet. We are climbing fast and we have barely begun. Above the MRI, the strongest steady magnetic fields ever made in a laboratory, using massive specialized equipment, reach a few million gauss, and only for brief instants. Push to the most extreme pulsed magnets, the ones that nearly tear themselves apart in the making, and you reach into the hundreds of millions of gauss. This is the ceiling of what human technology can do, the very top of the ladder we can build with our own hands. Now leave the Earth entirely. An ordinary neutron star, a standard pulsar like the one Jocelyn Bell found, carries a field near 1 trillion gauss. 1 trillion. That is already millions of times beyond the strongest magnet humans have ever made, even for an instant. We have left every earthly thing far below, and yet the ordinary pulsar is not the top of our ladder. It is only the rung just before the last. The magnetar's field is 1,000 trillion gauss. Take that trillion gauss pulsar, already millions of times beyond anything we can build, and multiply it by another 1,000. That is the magnetar. It stands above the fridge magnet by a factor of 10 trillion. The full climb, from the Earth's half a gauss to the magnetar's 1,000 trillion, spans a range so vast that no single image can hold both ends. Here is one way to feel it. If the Earth's field were the thickness of a single sheet of paper, then on the same scale the fridge magnet would be a short stack. The MRI would be the height of a person, the ordinary pulsar would reach far past the moon, and the magnetar would stretch a good fraction of the way to the nearest star. The steps are not even. Each one leaps far beyond the last. That is what we mean when we say nothing on Earth comes close. 1,000 trillion gauss is a different regime of nature, strong enough that the field stops being a thing that acts on matter and becomes a thing that remakes it. We have the number now. Next, we begin to see what it does to the world around it, starting with the strangest fact of all, that the field has mass. Here is a fact that sounds impossible at first. A magnetic field that's strong has weight. Not the object making it, the field itself, the invisible region of force around the star, carries real mass and pulls on things with gravity of its own. To see why, we need one of the most famous ideas in all of physics, the one Albert Einstein gave us, that energy and mass are two forms of the same thing. Einstein's relation says that energy equals mass times the speed of light squared. The deep meaning is that energy and mass are interchangeable. Anything that holds energy also has mass, and anything with mass holds energy. Usually we notice this only when mass turns into energy, as in the fusion that lights the sun or the fission in a reactor. But it runs the other way too. Pure energy, with no particles at all, still weighs something. A magnetic field holds energy. You know this already in a small way. A magnet can do work, it can pull a nail across a table, and the capacity to do work is energy stored in the field. The amount of energy in a field grows with the square of its strength. Double the field, and you quadruple the energy packed into each bit of space. The energy density climbs steeply as the field gets stronger. Now take that steep climb up to 1,000 trillion gauss. The energy stored in a magnetar's field is staggering, and because it climbs with the square of the strength, it dwarfs anything in a weaker field. Pack that much energy into the space around the star, apply Einstein's relation, and that energy carries a genuine, measurable mass. The empty-looking field around a magnetar weighs something real, and pulls with its own faint gravity. We can make this concrete. Near the surface of a magnetar, the energy in the magnetic field is so dense that, converted to mass by Einstein's relation, it would weigh far more than the same volume of lead. Think of that. The empty region of force just above the star's surface is, by weight, denser than solid metal, purely from the energy stored in the magnetism. There is nothing there but field, and yet it outweighs lead. This is not a trick of words. It has real consequences for the star. The field's energy is so concentrated that it presses on the star and helps shape it. A magnetar is not a perfect sphere. The colossal internal field strains the star from the inside, squeezing it slightly out of round, distorting the body of the city-sized object. The magnetism is no longer a passenger riding along on the star. It is heavy enough, energetic enough, to push the star around. This is the threshold we crossed without quite naming it. At ordinary strengths, a magnetic field is a thing that acts on matter, moving a compass needle, gripping a fridge. At 1,000 trillion gauss, the field has become a thing with substance, with weight, with the power to deform the star that holds it. It has crossed from being a property of matter to being almost a kind of matter in its own right, a presence dense enough to feel through gravity. And if the field is strong enough to outweigh lead and reshape a star, you might wonder what it does to the empty space around it. and to the few atoms and particles unlucky enough to be nearby? The answer is that this field is strong enough to change the rules that govern the smallest pieces of nature. It reaches the level where the quantum world itself, the behavior of electrons and even of empty space, starts to bend. There is a specific line where this begins, a critical strength, and a magnetar sits well past it. Physics has a special number, a particular magnetic field strength, where the quantum rules of nature begin to change. It is called the critical field, or the quantum critical field, and it sits at about 44 trillion gauss. Below this line, a magnetic field is strong but still ordinary in its behavior. Above it, the field is strong enough to interfere with the smallest workings of nature, and the world starts to behave in ways that have no everyday parallel. To understand where this line comes from, we have to look at the electron, the light, negatively charged particle that surrounds every atom. An electron in a magnetic field does not move freely. It is forced into a curving circular path, looping around the field lines. The stronger the field, the tighter and faster that loop. The energy tied up in that looping motion grows as the field grows. The critical field is the strength at which the energy of that looping motion becomes as large as the energy locked in the electron's own mass, its rest energy by Einstein's relation. At that point, the magnetic energy rivals the very substance of the particle. The quantum description of the electron, worked out in the theory called quantum electrodynamics, predicts that strange things begin once the field crosses this threshold. The smooth, familiar behavior of charged particles gives way to something governed by quantum rules at full strength. A magnetar's field of 1,000 trillion gauss is not just past this critical line, it is more than 20 times past it. The ordinary pulsar at 1 trillion gauss sits below the line in the tame regime. The magnetar sits far above it, deep in the territory where the quantum effects are not a small correction, but a dominant feature of how the star and its surroundings behave. This is the dividing line between a strong magnet and a magnetar, drawn by nature itself. Once you are above the critical field, several things change at once. The energy levels available to an electron become widely spaced rungs, called Landau levels, and the electron can only sit on certain rungs, not in between. This quantizing of the electron's motion reshapes how matter holds together, how light moves through the field, and even how the supposedly empty vacuum behaves. The field is now strong enough to reach into the quantum structure of nature and rearrange it. It is worth pausing on how rare it is for an astronomical object to cross a quantum line like this. Most of the cosmos, even the violent parts, operates in the everyday regime where quantum oddities stay hidden, averaged out across countless particles. A magnetar is one of the few places in the universe where a large, real object pushes a whole region of space past a fundamental quantum threshold and holds it there for thousands of years. It is a natural laboratory for physics we can almost never reach. This critical line is the gateway to everything strange that follows. Everything we're about to describe, the distortion of atoms, the bending of light in empty space, the lethal reach of the field, all of it happens because a magnetar lives so far above this threshold. Below the line, the field is powerful but well behaved. Above it, the rules loosen, and the field begins to do things that sound like fantasy, but are simply physics carried to an extreme. We have now built the full foundation. We know what a magnetar is, how it forms, how strong its field is, that the field has weight, and that it sits deep in the quantum regime past the critical line. From here on, we stop building the object and start exploring what it does. We begin with the matter near the surface, with ordinary atoms caught in a field above the critical line, and what becomes of them when chemistry itself can no longer hold its usual shape. Start with a single atom, a hydrogen atom, the simplest there is. It is one proton at the centre with one electron around it, and that electron is not a tiny ball in orbit. It is a soft, round cloud of probability, spread evenly in all directions, a fuzzy sphere of presence around the nucleus. That round shape is the foundation of all chemistry. the way atoms bond, the way molecules form, the shape of every material, all of it rests on the roughly spherical clouds of electrons around atoms. Now place that atom in a magnetar's field. Above the critical line, the field seizes the electron cloud. Remember that an electron in a strong field is forced to loop around the field lines, and the stronger the field, the tighter the loop. At 1,000 trillion gauss, the loops are squeezed so tight that the electron can barely move sideways across the field at all. It is free to move only along the lines, back and forth like a bead on a wire. The round cloud is gone. In its place, the atom becomes a thin needle, a long narrow cylinder of electrons stretched out along the field direction. Calculations show that a hydrogen atom in a magnetar's field would be squeezed sideways to perhaps 1/200th of its normal width, while keeping its length, so it stands as a slender spike instead of a ball. The atom has been reshaped from a sphere into a splinter. This breaks chemistry as we know it. Chemistry depends on those round electron clouds reaching out and overlapping to form bonds. When every atom is squeezed into a thin needle aligned with the field, the rules change entirely. The needle-shaped atoms can link end to end along the field lines, forming long chains, like beads strung in a row. Matter near a magnetar's surface is thought to organize itself into these magnetic polymer chains, a form of matter that exists nowhere on Earth and cannot exist outside such a field. These chains bind together far more tightly than ordinary matter. Stacked side by side, the chains form a surface far stronger and stiffer than any normal solid, a crust of needle atoms held in rigid array by the field. The everyday solids you know, metal and stone and bone, are loose and soft compared with matter compressed into this magnetic form. The field has not just bent the atoms, it has forged them into a new kind of material with its own strange strength. The reshaping reaches the light the atoms give off as well. An atom emits and absorbs light at particular colours, set by the energy steps its electron can take. Squeeze the atom into a needle and those energy steps change, so the colours shift. Light that would normally come off at one wavelength comes off at another, pushed and rearranged by the field. The fingerprint of an element near a magnetar is not the fingerprint we measure in a laboratory. The field rewrites even the spectrum of light. There is something humbling in this. Chemistry feels permanent to us, a fixed set of rules baked into the world, the periodic table on the classroom wall. But those rules are not absolute. They hold because we live in a place where magnetic fields are gentle and atoms can keep their round shape. Turn the field up high enough, and chemistry itself bends. The round clouds collapse into spikes, and matter reorganizes into forms we will never hold in our hands. And the field does not stop at matter. It reaches into the emptiness between things. We tend to think of empty space as the one truly inert backdrop, a stage on which events happen, but which does nothing itself. Near a magnetar, even that is not true. The vacuum, the pure nothing around the star, responds to a field this strong and begins to behave like a strange transparent crystal, bending light in a way empty space has no business doing. That is the next strange thing the field does. We think of empty space as nothing. Remove every atom, every particle, every speck of dust, and what is left should be a perfect void that does nothing and affects nothing. Light should pass through it unchanged. For almost every place in the universe, that is exactly right. But quantum physics tells us the vacuum is not truly empty, and near a magnetar that hidden structure shows itself. According to quantum theory, the vacuum constantly seethes with pairs of particles that flicker into being and vanish again, far too quickly to catch. An electron and its opposite, a positron, can appear together, exist for the briefest instant, and annihilate back into nothing. This is not a fantasy. The faint effects of these fleeting pairs have been measured in delicate experiments on Earth. Empty space is filled with this quiet, restless flickering, normally far too subtle to notice. A strong magnetic field acts on these flickering pairs while they briefly exist, because they are charged. In a magnetar's field, The constant flicker of electron-positron pairs is bent and organised by the field, and this gives the vacuum itself a structure, a grain, an alignment. The empty space around the star is no longer the same in every direction. It now has a preferred axis, set by the field, like the grain in a piece of wood. When space has a grain, light passing through it behaves strangely. This effect is called vacuum birefringence, and the word birefringence describes a material that bends light differently depending on how the light is oriented. Certain crystals on Earth do this. A clear crystal of calcite laid on a page splits the text beneath it into two overlapping images because it bends light two ways at once. A magnetar's field makes the empty vacuum behave like such a crystal. So near a magnetar, the void itself becomes optically active. Light of one orientation travels slightly differently from light of another, just as it would inside a calcite crystal, except here there is no crystal, only field-charged emptiness. Pure nothing, given a grain by the most intense magnetism in the universe, splits and shapes the light that crosses it. This was predicted from quantum theory decades ago as one of its strangest consequences, almost impossible to test, because no laboratory field comes anywhere close to strong enough. A magnetar offered the first real chance to see it. In 2016, a team of astronomers studied the light from a quiet, isolated neutron star using a large telescope, measuring how the light was oriented as it came to us. They found that the light was aligned in a particular way, organised to a degree that ordinary physics struggled to explain, but that vacuum birefringence predicted neatly. It was the first observational sign that empty space near such a star really does behave like a birefringent crystal. The result was a faint signal, drawn from the light of a small dim star far away, and scientists were careful to call it evidence rather than final proof. Measuring the polarization of light from such a distant, faint object pushes a telescope to its limits, and the work continues with newer instruments. But the prediction and the observation pointed the same way, toward a vacuum that is not inert near a magnetar but shaped and grained by the field, bending light as no empty space should. Sit with that for a moment. The strongest magnets in the universe do not only crush atoms into needles, they reach into nothing itself and give it a texture so that the void bends light. The field's influence does not require any matter to act on. It acts on the bare structure of space. This is the deepest sign of how far past ordinary physics a magnetar reaches. And it begins to explain why getting close to one is not merely dangerous but impossible. Why the field alone, before any heat or radiation, would already be lethal from a vast distance. We have built the magnetar up piece by piece, and now we can answer the second half of the title plainly. Why does nothing survive near one? The answer begins with the field alone, before we add heat, before radiation, before gravity. The magnetic field by itself, simply by being as strong as it is, would destroy any living thing and any ordinary matter from an enormous distance away. Start with your own body. You may not think of yourself as magnetic, but every atom in you responds to a magnetic field, if only faintly. The water that makes up most of your body, the proteins, the cells, all of it is built from atoms whose electrons and nuclei feel a magnetic pull. In the gentle fields of Earth, this response is so tiny you never notice it. In a strong enough field, it becomes overwhelming. Bring a human body anywhere near a magnetar, and the field would reach into every molecule at once. The electron clouds that hold your atoms together would be squeezed, just as we saw, deformed from round into elongated shapes. The chemistry that runs every cell, every nerve signal, every strand of the molecules that carry your genetic code depends on those clouds keeping their normal form. Distort them, and the chemistry of life simply stops. The molecules can no longer do what they do. How far out does this reach? The field of a magnetar weakens with distance, falling off steeply as you move away, but it starts so monstrously high that even far away it remains beyond lethal. Estimates put the deadly range at roughly 1,000 kilometers, and by some measures far more. From 1,000 kilometers away, the field would already be strong enough to disrupt the chemistry of your body. You would be killed by magnetism alone, at a distance greater than the width of many countries, without ever touching the star. It is worth being clear about how unusual a way to die this is. We're used to dangers that act through force or heat or poison, things that push or burn or interfere with the body's machinery from outside. The Magnetar's field does something stranger. It reaches inside into the structure of your atoms and unmakes the molecules directly. There is no shielding against it, no material that blocks it, because the field passes through everything and acts on the atoms of the shield as readily as the atoms of you. This is the outer edge of the death zone, the region where the field alone is fatal, and it surrounds the star for 1,000 kilometers or more in every direction. To put that in scale, it is a sphere wider than the Magnetar itself by 100-fold, a vast invisible zone of lethality with the small, dense star at its heart. Nothing made of ordinary atoms could cross that boundary and remain what it was. The field would have rewritten it long before it arrived. And we have only spoken of the field, the gentlest of the Magnetar's weapons. We have not yet added the searing heat radiating from a surface still glowing at 1,000,000 degrees. We have not added the storm of X-rays and gamma rays streaming off the star. We have not added the crushing gravity, 100 billion times Earth's, or the tidal force that comes with it. Each of these alone would be deadly. Together they make the space around a Magnetar one of the most hostile places that exists. So picture an object falling inward from far away, crossing that 1,000-kilometer line where the field first turns lethal, and then continuing down toward the surface through everything else the star can do. What happens to it as it falls is worth tracing step by step, because it shows just how many ways a Magnetar has to take a thing apart, and how little of the original would be left by the end. Imagine dropping something toward a Magnetar. Not a person, that is too grim, but say a small spacecraft, a probe of metal and instruments, falling inward from far out in space. Trace its fall step by step and you see every weapon the star carries come into play, one after another, each more violent than the last. Long before the probe reaches the surface, it stops being a probe at all. First, far out, the magnetic field takes hold. We just saw that the field turns lethal to living chemistry around 1,000 kilometers away. For a machine, the field does its own damage. Any electric current in the probe circuits feels the field and is twisted by it. Any moving charge is pushed sideways. The electronics would scramble and fail. The materials would begin to feel the strain of their own atoms being deformed. The probe is already dying as a working machine while still far from the star. Next comes the radiation. A Magnetar pours out X-rays and gamma rays, the most energetic light there is, streaming from its hot surface and its active field. As the probe falls closer, this radiation grows fierce, then unbearable. The high-energy light tears through the probe's materials, knocking electrons loose, breaking the bonds that hold solids together. The surface of the probe would heat, char, and start to come apart under the flood of energy long before it arrives. Then the gravity asserts itself, and with gravity comes tidal force. Tidal force is the difference in gravity's pull between the near side of a falling object and its far side. Near a normal planet, this difference is gentle, the same effect that raises ocean tides on Earth. Near a Magnetar, with gravity 100 billion times stronger than Earth's, the difference across even a small object becomes savage. The near end of the probe is pulled far harder than the far end. That difference would stretch the probe lengthwise and squeeze it sideways at the same time, a process grimly nicknamed spaghettification, because anything falling in is drawn out into a long, thin strand. The probe, then whatever is left of it, would be pulled apart not by hitting anything but simply by the unequal grip of gravity along its length. Bolts would part, frames would stretch, the machine would be drawn into a lengthening thread of matter falling toward the star. By now the probe is no longer an object. It is a stream of its own atoms, ionized by the radiation, stripped and stretched, spiraling down along the magnetic field lines. the field channels charged matter so the remains do not fall straight in. They are funneled along the lines toward the magnetic poles, guided down onto the star in a tight glowing column, the way a magnetar feeds on any matter that strays too close. When that column of matter strikes the surface, falling under a gravity 100 billion times Earth's, it arrives at a sizable fraction of the speed of light. It slams into the crust and releases its energy as a final flash of X-rays. The last trace of the probe announces itself as a brief glow at the magnetic pole, and then it is gone, merged into the star, indistinguishable from the rest of the matter that makes up the city-sized sphere. That is the journey in. Field, radiation, tidal force, and the funneling fall to the surface, each stage tearing the object down further until nothing recognizable remains. We have traced the death zone from its outer edge all the way down. Now it is time to set foot carefully on the star itself, on that solid crust the funneled matter crashes into, and see what kind of surface could hold a field this strong without flying apart. We have called the Magnetar's surface a crust, and that word deserves a closer look, because the crust of a neutron star is unlike any solid you have ever met. Beneath it, the star is thought to be a strange fluid of neutrons, a kind that flows with no friction at all. But the outermost layer, perhaps a kilometre or two thick, is solid. It is the lid on the star, and it is the stage on which the Magnetar's most violent events play out. This crust is made of the matter we described earlier, atomic nuclei crushed close together, with free electrons running among them, all packed at densities far beyond anything on Earth. Near the surface it is mostly heavy nuclei like iron, squeezed into a rigid lattice. Deeper down the nuclei grow more and more neutron-rich, until they dissolve into the neutron fluid below. The crust is the frozen skin over an ocean of neutrons. Its strength is almost beyond belief. Studies of neutron star crust suggest it is the strongest material in the universe, something like 10 billion times stronger than steel. To bend or break it would take forces that no ordinary process could supply. The crust holds its shape against the star's own staggering gravity, and stays rigid where any earthly material would have flowed or shattered long ago. It is a solid built under pressures that rewrite what solid means. Now lay the Magnetar's field across this crust. The field does not float free above the star. It is anchored deep inside, threaded through the crust and the interior, its lines locked into the charged matter. The field and the crust are bound together, so the field cannot easily move without moving the crust, and the crust cannot move without dragging the field. They are welded into a single system, the most rigid solid in the universe, holding the strongest magnetism in the universe in a tight grip. Here is where the trouble builds. The colossal field is not content to sit still. Its energy strains to rearrange itself into a lower, more relaxed configuration, the way a wound spring strains to unwind. The field pushes and pulls on the crust from within, trying to shift, twisting against the rigid lattice. But the crust, strong as it is, holds the field in place, refusing to let it move. Stress builds in the crust, year after year, like a fault line being slowly loaded. This is the same physics as an earthquake, scaled up beyond imagination. On Earth, the slow grinding of tectonic plates loads stress into rock along a fault, and the rock holds until it cannot, then slips all at once in a quake. On a magnetar, it is the magnetic field that loads the stress, building pressure on the rigid crust until the crust can no longer bear it. The strongest material in the universe is being strained by the strongest field in the universe, and one of them must eventually give. For a long time the crust wins, holding firm, absorbing the strain, but the field is patient and relentless, and the stress only grows. The crust can flex a little, but it cannot flex forever. Somewhere a region reaches its limit, the point where even 10 billion times steel can hold no more. When that moment comes, the crust does what stressed rock does on Earth. It cracks. It fails suddenly and violently in an event that has earned its own name. What happens in that instant of failure is one of the most powerful events the nearby universe ever sees. A sudden release of energy that can outshine anything for light years around. To understand the bursts and giant flares that make Magnetars famous, we have to watch the crust break and watch the field above it snap into a new shape in response. That is the starquake. When a Magnetar's crust finally cracks, the event is called a starquake, and it is an earthquake only in the loosest sense because the energy it releases dwarfs anything our planet could ever produce. A single starquake can unleash, in a fraction of a second, more energy than the sun pours out in many thousands of years. The ground that shifts is the strongest material in the universe, and the force that shifts it is the strongest field. Picture the moment of failure. For years, stress has built in the crust as the field strained to rearrange itself. Now a patch of crust reaches its breaking point and gives way, shifting by perhaps a few centimeters. That sounds tiny, a movement smaller than the width of your hand. But it is a few centimeters of the most rigid, densest solid that exists, driven by the most powerful magnetic force that exists, and the energy stored in that strain is colossal. A shift of centimeters releases the fury of a star. The crucial part is what happens to the field above the surface. The field lines are anchored in the crust, their feet planted in the solid lattice. When the crust cracks and shifts, it drags the feet of those field lines with it, yanking the whole towering structure of the field above the star into a new arrangement. The field, suddenly disturbed, snaps and reconnects into a lower energy shape, and in doing so it dumps a vast amount of stored magnetic energy all at once. That released energy goes into the thin gas of charged particles just above the star, heating it instantly to temperatures beyond imagining and accelerating it to enormous speeds. The result is a fireball of superheated matter and radiation, trapped on the field lines, glowing fiercely in X-rays and gamma rays. The starquake on the surface and the snapping of the field above it together produce a sudden, brilliant burst of high-energy light that races out across space. This is the source of the burst that first revealed Magnetars, the soft gamma repeaters firing again and again. Each burst is a starquake, a moment when the crust fails somewhere and the field rearranges, lighting up the star. Most are relatively small, brief flashes lasting a fraction of a second, releasing the kind of energy that, while staggering by human measure, is modest for a Magnetar. These small bursts come often, sometimes in flurries, the everyday activity of a restless star. The connection between the crust and the field explains why Magnetars are so much more violently active than ordinary neutron stars. An ordinary pulsar has a weak field that exerts little strain, so its crust sits quiet, rarely cracking. A Magnetar's field is 1,000 times stronger, straining the crust constantly, cracking it again and again, and carrying 1,000-fold more energy to release when it does. The strength of the field drives the whole cycle of stress, failure, and burst. There is a feedback to it as well. Each starquake relaxes the field a little, releasing some of its pent-up energy, but the field is so vast that one quake barely touches the total. The stress soon builds again, the crust strains again, and another quake follows in time. Over thousands of years, through countless quakes, the Magnetar slowly bleeds its magnetic energy away, burst by burst, until at last the field has weakened enough that the cracking stops and the star falls silent. So the ordinary bursts are the small, frequent voice of the Magnetar, the everyday speech of a star under magnetic strain. They are how these objects first spoke to us, in flashes of gamma rays from across the galaxy. But every so often, far more rarely, a Magnetar does not merely crack a patch of crust. It convulses on a scale that makes the ordinary burst look like whispers, in an event so powerful it can be felt across the entire galaxy and beyond. Most of what a Magnetar does is small, by its own enormous standards. The frequent bursts, the flickers of gamma rays, the brief flashes that earn the soft gamma repeaters their name. These are the routine business of the star, a patch of crust cracking, a small rearrangement of the field. They happen often, and while each would be catastrophic up close, from across the galaxy they register as modest blips. This is the Magnetar talking quietly to itself. These ordinary bursts are worth dwelling on because they are the steady background of a Magnetar's life. A soft gamma repeater can fire off dozens or hundreds of small bursts in an active spell, sometimes clustered into storms where bursts come one after another for hours. Each lasts a fraction of a second. A sharp spike of soft gamma rays then fades. The star quiets, then fires again. For months or years it may fall silent, then wake into a new round of activity. The energy in one of these small bursts is, by human measure, immense, yet for a Magnetar it is almost nothing, a tiny fraction of the energy stored in the field. The star has a reservoir so vast that it can fire these bursts for thousands of years without coming close to exhausting it. We are watching a slow, patient discharge, the field shedding its energy in small increments, crack by crack, flash by flash, across the long active life of the star. For a long time, these ordinary bursts were all astronomers knew of the soft gamma repeaters, and they shaped the early picture of these objects. The bursts were how the sources were found, how they were catalogued, how their slow spins were measured. They were the Magnetar's signature, the repeated flashing that told us something strange and powerful sat at that point in the sky, releasing energy no ordinary neutron star could. But the small bursts are not the limit of what a Magnetar can do. Very rarely, perhaps once in decades for any given star, a Magnetar does something far more violent. Instead of a small patch of crust cracking, a huge region fails at once, and the field undergoes a massive global rearrangement rather than a local one. The energy released is not a small fraction of the field's store, but a substantial chunk of it, all at once. These rare, colossal events are called giant flares, and they stand apart from the ordinary bursts the way a great earthquake stands apart from a faint tremor. A giant flare can release in a fraction of a second as much energy as the sun emits in 100,000 years or more. It is among the most luminous events known in the universe short of the death of a star. A single neutron star briefly outshining entire galaxies in gamma rays. Only a few giant flares have ever been recorded because they are so rare and because a Magnetar must be close enough in galactic terms for us to catch one clearly. Each one that has been seen became a landmark event, studied intensely, because it offered a rare look at a Magnetar pushed to its absolute limit, releasing its energy not in a whisper, but in a scream. These events also carry a sobering lesson about just how far a Magnetar's reach extends. The first of the great flares to be studied in real detail came in 1998 from a Magnetar with the catalogue name SGR 1900+14. It was powerful enough that its effects swept across the entire solar system and were felt at the Earth, from a star thousands of light years away. To understand what a giant flare really means, and how a dead star so far off could reach across all that distance and touch our own planet, we should look closely at that event. On the 27th of August 1998, a wave of gamma rays and X-rays washed over the solar system from a Magnetar called SGR 1900+14, lying roughly 20,000 light-years away in our galaxy. It was a giant flare, one of the first ever caught in detail, and it briefly made this distant dead star one of the brightest gamma-ray sources the inner solar system had ever recorded. The energy that arrived had travelled for 20,000 years to reach us. The flare had the structure these events typically show. It began with a sudden, ferocious spike, an initial blast of hard radiation lasting under a second, so intense it saturated the detectors on several spacecraft. Then came a longer tail, a glowing aftermath that faded over several minutes, and through that fading tail ran a steady pulse. The pulse beat once every 5 seconds or so, the spin period of the star, as the rotating Magnetar swept its glowing, flare-heated regions past the Earth. That pulsing tail was a gift to astronomers, because it confirmed the picture so cleanly. The 5-second beat was the rotation of the neutron star, and the slow fade was the trapped fireball of superheated plasma held on the field lines, cooling as the star turned. Watching the flare pulse and fade, scientists could read the spin of the star and see the field doing exactly what theory said, holding a vast cloud of radiating plasma captive above the surface. The power of the event is hard to convey. In its first fraction of a second, the flare released more energy than the sun emits in many thousands of years, from an object only about 20 kilometers across. All of that came from the magnetic field, suddenly rearranging after a massive failure of the crust, dumping a piece of its colossal energy store into radiation in an instant. It was the field unwinding violently and lighting up the galaxy as it did. What made this flare famous, though, was not only its power, but its reach. 20,000 light-years is a vast distance, more than the span from the Earth to the centre of the galaxy. Across that immense gulf you would expect a dead star's flash to arrive faint and harmless, a signal for instruments and nothing more. Instead, this flare arrived with enough force to physically disturb our planet, to reach across 20,000 years of empty space and leave a mark on the Earth itself. The mark was on the upper atmosphere. Earth is wrapped in a layer called the ionosphere, a region high up where the sun's radiation strips electrons from atoms, leaving a sea of charged particles. The ionosphere swells and shrinks with the day, ionized by sunlight, settling at night. It is the layer that reflects radio waves and lets distant stations carry over the horizon. It responds to incoming radiation, and normally that radiation comes from the sun. When the giant flare's radiation struck, it ionized the Earth's upper atmosphere as if a burst of extra daylight had arrived in the dark. Detectors on the planet's night side, where the ionosphere should have been quiet and settled, registered a sudden change, the upper atmosphere lurching as though the sun had momentarily risen. A dead star 20,000 light-years away had reached across the galaxy and briefly rearranged the air high above the night side of the Earth. Sit with the strangeness of that. A neutron star so far away that its light takes 20,000 years to arrive. An object the size of a city, long dead, still managed to disturb the atmosphere of a living planet across that entire distance. It is one of the clearest demonstrations of just how much energy a magnetar holds. And remarkably, the 1998 flare was not even the largest we have seen. A few years later, a closer magnetar would unleash something greater still. On the 27th of December, 2004, the most powerful giant flare ever recorded swept through the solar system, from a magnetar named SGR 1806-20, lying somewhere around 40 to 50,000 light-years away on the far side of our galaxy. It was the brightest burst of light from beyond the solar system ever measured at the Earth, brighter in that instant than anything outside the sun had ever been recorded to be. The numbers attached to this flare-strain belief. In 0.2 of a second, the star released more energy than the sun gives off in 100,000 to 250,000 years. All of it poured out in that 1/5 of a second from a single neutron star on the other side of the galaxy. For that brief moment, this one dead star outshone the entire rest of the Milky Way combined in gamma rays, a single point blazing brighter than 400 billion other stars. Think about the distance again. SGR 1806-20 sits perhaps 40,000 light-years away or more, far across the galaxy, nearly on the opposite side from us. Light from it has travelled some 40,000 years to arrive, and yet across all that distance the flare struck the Earth hard enough to produce clear physical effects on our planet, just as the 1998 flare had, but stronger, because for all its greater distance this flare was simply far more powerful. The radiation hit the Earth's ionosphere and disturbed it sharply, more than the earlier flare had despite the greater range. Instruments around the world registered the sudden ionization of the upper atmosphere. Spacecraft detectors were saturated, swamped by the intensity. Some were briefly blinded, their readings driven off the scale by a flood of gamma rays from a star so far away its light belonged to the deep past. The flare announced itself unmistakably across every instrument that could see that part of the sky. There is a sobering thought in this. The flare did no harm to life on Earth because the Magnetar was tens of thousands of light years away. But scientists worked out what would happen if such a flare went off much closer, within a few light years of the Earth. The answer is that it could seriously damage the ozone layer, the thin shield high in our atmosphere that blocks the sun's harmful ultraviolet light. A nearby giant flare could strip away a large part of that protection in moments. Fortunately, no Magnetar sits anywhere near that close. The nearest known ones are thousands of light years away, far too distant to threaten us. Giant flares of this size are also rare, only a few seen in decades of watching the whole sky. The combination of distance and rarity means a Magnetar is no danger to the Earth in any practical sense. But the 2004 flare made vivid what these objects are capable of, the sheer scale of the energy a magnetic field can store and release. The flare also taught astronomers something new. By studying its initial spike and the way the energy was released, they refined their picture of how a giant flare works, confirming that it comes from a global rearrangement of the field after a large-scale failure of the crust, rather than the small local cracks that make the ordinary bursts. The 2004 event was the clearest window yet into a Magnetar at its most extreme, the field unwinding in a single colossal convulsion. That a star so far away could reach across the galaxy and touch our sky, twice now, says something about the place these objects hold in the universe. Their influence does not stay local. It crosses tens of thousands of light years and brushes against a small blue planet. And the way these stars wind down, slowing and quieting over time, gives their power a natural end. To understand why Magnetars are only briefly so violent, we turn to the brakes that slow them. A Magnetar is not violent forever. Its life of bursts and flares is brief, by the measure of stars, lasting only about 10,000 years before the object falls quiet. To see why the active phase is so short, we return to the spin, and to the way the field acts as a brake, bleeding away the star's rotation, and, with it, the conditions that make a Magnetar a Magnetar. Recall that a neutron star is born spinning fast, sometimes hundreds of times a second, wound up by the collapse that made it. Recall too that the magnetic field is anchored in the star and turns with it. A spinning magnet sweeping through the thin gas and radiation around it drags against its surroundings, and that drag acts as a brake. The star loses rotational energy steadily, and its spin slows. This is magnetic braking, and it works on every neutron star. The strength of the braking depends sharply on the strength of the field. A weak field grips its surroundings only loosely and slows the star gently, over a very long time. A strong field grips hard and brakes fiercely. A Magnetar, with a field 1,000 times stronger than an ordinary pulsar, brakes a great deal harder, so it sheds its spin far faster than a normal neutron star ever would. This is why Magnetars spin so slowly when we find them. The numbers tell the story. An ordinary pulsar may keep spinning many times a second for millions of years, slowing only gradually. A Magnetar, braked by its monstrous field, slows from a rapid newborn spin to a sluggish rotation of once every few seconds in just a few thousand years. By the time we catch one as a soft gamma repeater, turning once every 5 or 8 seconds, it has already been braking hard for thousands of years, and it is well into middle age for an object of its kind. This rapid spin down was one of the clues that confirmed the Magnetar idea in the first place. When Chryssa Kouvelioutou's team measured how fast SGR 1806-20 was slowing, the rate was so high that only a field of 1,000 trillion gauss could explain it. The brake was so strong that the field behind it had to be enormous. The very thing that ends a Magnetar's active life was the thing that proved how powerful it was. The braking also sets the clock on the bursts and flares. Those events are powered by the field straining against the crust, and as the field winds down over time, its grip weakens, the strain eases, and the crust cracks less often. After 10,000 years or so, the field has decayed enough that the violent activity fades. The starquakes grow rare, the bursts stop, and the magnetar settles into quiet. It does not vanish, but it goes silent. What remains is still a neutron star, still dense, still spinning slowly, but no longer the raging object it was. Its field, though weakened, is still strong by any ordinary measure, perhaps still above 1 trillion gauss for a long time after. But the era of giant flares and frequent bursts is over. The Magnetar has spent the most violent portion of its magnetic energy, and it joins the vast, quiet population of old neutron stars drifting through the galaxy, their fiercest days behind them. This short, brilliant active life has a consequence for how many magnetars we can see. Because a magnetar is only active for about 10,000 years, a brief window in cosmic time, only the youngest ones are caught in the act of bursting. The galaxy may hold a great many old, quiet magnetars, long since faded for every active one we detect. But every so often, a quiet magnetar surprises us by speaking again, in a way that has connected these stars to one of the great mysteries of modern astronomy. In April of 2020, a Magnetar in our own galaxy did something that linked these objects to a puzzle astronomers had been chasing for over a decade. The Magnetar was named SGR 1935 plus 2154, sitting around 30,000 light-years away. It had been known as an ordinary, if restless, Magnetar, firing its usual bursts of X-rays and gamma rays. Then it produced something new, a brief brilliant flash of radio waves, and that flash changed the story. To see why the radio flash mattered, we need the puzzle it spoke to. Since 2007, astronomers had been detecting strange signals from deep space called fast radio bursts. A fast radio burst is an intense flash of radio energy, lasting only 1,000th of a second or so, arriving from far across the universe, often from galaxies billions of light-years away. In that brief flash, a fast radio burst can release as much energy as the sun puts out in days, and for years no one knew what produced them. Fast radio bursts were one of the genuine mysteries of modern astronomy. They were clearly powerful, clearly distant, and clearly common, with thousands of them flashing across the sky. But because they were so brief and so far away, pinning down their source was extraordinarily hard. Many ideas were floated, from colliding neutron stars to exotic processes no one had seen. A leading suspicion was that magnetars might be responsible, but there was no direct evidence tying the two together. Then came the burst from SGR 1935 plus 2154. In April 2020, this Magnetar emitted a flash of radio waves so bright that, although it came from within our own galaxy, it was comparable in character to the fast radio bursts seen from distant galaxies. It was as if one of the mysterious distant flashes had gone off in our own backyard, close enough to study in detail and to trace, unmistakably, to a known magnetar. This was the long-sought link. For the first time, a fast radio burst-like flash had been caught coming from an identified object, and that object was a magnetar. The radio flash arrived alongside a burst of X-rays from the same star, tying the radio emission directly to the magnetar's known activity. It strongly suggested that at least some of the fast radio bursts crossing the universe are produced by magnetars, by these same star quakes and field rearrangements seen from far enough away that only the radio flash reaches us clearly. The discovery did not solve the fast radio burst mystery completely. The flash from our galactic magnetar, while bright, was still less energetic than the most powerful distant bursts, so it is likely that magnetars produce fast radio bursts through processes that can vary widely in strength, or that more than one kind of event is involved. The picture is still being assembled, but the central link, magnetar to fast radio burst, was now established by direct observation. It was a striking moment of connection. A class of object discovered in our galaxy through gamma-ray bursts turned out to be tied to a class of signal discovered across the universe through radio flashes. The magnetar, already strange enough on its own, now stood revealed as a likely engine behind one of the most far-reaching mysteries in the sky. its bursts detectable not just across our galaxy, but, in their grandest form, across much of the observable universe. This deepens the importance of understanding magnetars, because they may be lighthouses we can see from enormous distances, beacons that tell us about space far beyond our reach. And it raises a natural question. If these objects are so powerful and so far-reaching, how many of them are there? How common is a magnetar in our galaxy and beyond, and where is the nearest one to us? How many magnetars are there? The honest first answer is that we know of only a small number directly, around 30 confirmed magnetars catalogued in and around our galaxy. That is a tiny number against the hundreds of billions of stars the Milky Way holds, and against the many hundreds of ordinary pulsars we have found. By a simple count of what we have seen, magnetars look rare, a handful of exotic objects scattered across the sky. But that count is badly misleading, and the reason takes us back to their short lives. A magnetar is active, bursting and flaring and shining in X-rays for only about 10,000 years before its field winds down and it goes quiet. 10,000 years is the blink of an eye in cosmic time, so the magnetars we detect are only the very youngest ones, the ones still in their brief active phase. For every active magnetar we see, there should be a great many old, quiet ones we cannot. When astronomers account for this, estimating how many magnetars must have formed over the long history of the galaxy to explain the few active ones we catch now, the numbers grow enormous. The galaxy may hold tens of millions of magnetars, the vast majority of them old and silent, their fierce days long past, drifting unseen among the stars. We see only the freshly born ones still flaring. The dark, quiet population dwarfs the visible one. This means magnetars are not the rare curiosities the raw count suggests. They may be a substantial fraction of all neutron stars, perhaps something like 1 in 10 of the neutron stars born in supernovae, by some estimates even more. A large share of the massive stars that die and leave neutron stars behind may produce magnetars, depending on how fast their cores happened to be spinning when they collapsed. The conditions for the dynamo may be more common than first thought. There is one magnetar that holds a special place because of where it sits. Near the very centre of our galaxy, close to the supermassive black hole that anchors the Milky Way, lies a magnetar known by the catalogue name SGR-J, 1745-29. It orbits in the crowded extreme environment of the galactic centre, the closest known magnetar to the black hole at the heart of our galaxy, a lighthouse burning in the most turbulent neighbourhood the Milky Way has. That magnetar near the centre has been valuable to astronomers for a reason beyond its location. As its radio waves travel to us through the matter near the galactic centre, the signal is shaped by what it passes through, carrying information about the environment around the central black hole. A magnetar there acts as a probe, a beacon whose light tells us about a region we can scarcely study any other way. The strangeness of these objects makes them useful, not just spectacular. As for the nearest magnetar to Earth, the closest known ones lie a few thousand light-years away, comfortably distant. There is no magnetar near enough to pose any threat to us, and given how the galaxy is arranged, that is unlikely to change for an extraordinarily long time. The death zone of even a giant flare, lethal as it is, reaches its catastrophic worst only over light-years, and no magnetar sits anywhere near that close. We can study them in safety, from afar. So the galaxy is quietly full of these objects, mostly dark, occasionally flaring, a hidden population of the strongest magnets in existence. Their numbers and their power together hint at a larger role in the cosmos. If magnetars are common, and if each can release energy on the scale of a giant flare, then they may be doing more than lighting up now and then. They may be the hidden engines behind some of the brightest and most violent events the universe produces. A magnetar is born in a supernova, the explosive death of a massive star. For most of this story, we have treated that supernova as the beginning, the event that makes the magnetar and then ends. But there is a growing idea that turns this around, that in some cases the newborn magnetar is not just a leftover of the explosion, but the engine that drives it, the hidden power source making certain supernovae far brighter than they should be. Most supernovae are powered by the explosion itself, the shock wave and the radioactive material flung out in the blast glowing as it decays. But astronomers have found a class of exceptionally bright explosions called superluminous supernovae that shine 10 or 100 times brighter than ordinary ones, far too bright for the usual mechanisms to explain. Something extra must be pumping energy into these explosions, some central engine adding power the ordinary blast cannot supply. A leading candidate for that engine is a newborn Magnetar with a very fast spin. Imagine a Magnetar born spinning hundreds of times a second, holding an immense store of rotational energy on top of its colossal field. As its powerful field breaks that rapid spin, it bleeds the rotational energy out quickly, over weeks and months, and pumps it into the expanding cloud of debris from the supernova. That injected energy could light the debris far brighter and longer than the blast alone, producing a superluminous supernova. The timing fits neatly. A young Magnetar with a fast spin sheds its rotational energy on roughly the same timescale, weeks to months, over which these bright supernovae rise and fade. The Magnetar acts like a battery placed at the centre of the explosion, releasing its stored spin energy into the surrounding gas at just the rate needed to keep it glowing. Where an ordinary supernova fades, one with a Magnetar engine inside is kept burning bright by the spinning star at its heart. The same idea reaches toward another of the universe's great explosions, the gamma-ray burst. Gamma-ray bursts are the most luminous explosions known, brief and staggeringly powerful flashes of gamma rays from distant galaxies, thought to mark the births of black holes or neutron stars in special, violent collapses. Some gamma-ray bursts have features that a newborn, rapidly spinning Magnetar could help explain, its energy shaping or extending the burst in ways a simple collapse might not. In this picture, a Magnetar formed in a particularly extreme collapse could drive a jet of matter and energy outward, helping to power the gamma-ray burst, or could prolong its glow with the energy of its spin and field. Not all gamma-ray bursts need a Magnetar, and the details are debated, but for some of them the newborn Magnetar is a strong candidate for part of the engine. The same object that ends its life flaring quietly in our galaxy may begin it powering one of the brightest events in the cosmos. This casts Magnetars in a far larger role than their small size suggests. An object the width of a city, born in the collapse of a star, may be capable of outshining whole galaxies, not only in the rare giant flares of its old age, but in the very explosion that creates it. The Magnetar would then be not a curious byproduct of stellar death, but a central actor in some of the most extreme events the universe stages. These ideas are still being tested, and that is the honest state of the field. Some superluminous supernovae and some gamma-ray bursts may be Magnetar-powered. The evidence is suggestive, and the case has grown stronger over the years, but it is not settled. That uncertainty is not a weakness in the story. It is the live edge of it, the place where the science is still being worked out, and there are other open questions about Magnetars, just as deep, that remain genuinely unanswered. For all that we have learned about Magnetars, the honest truth is that much remains unknown, and it is worth ending the science not with the settled parts, but with the open ones, the questions astronomers are still working to answer. A Magnetar is an object at the very limits of physics, and at those limits our understanding naturally thins. Several real puzzles remain, and they sit at the heart of how these objects form and behave. The deepest open question is how Magnetars get their fields in the first place. We have told the dynamo story, the idea that a fast-spinning newborn neutron star churns and amplifies its field 1,000-fold in the first seconds of life. That is the leading explanation, and it is elegant, but it is not the only one, and it is not proven. There is a serious competing idea, and the choice between them is still being argued. The competing idea is called the fossil field hypothesis. It proposes that a Magnetar's enormous field is not built fresh by a dynamo after birth, but is inherited directly from the parent star. Some massive stars are observed to have unusually strong magnetic fields of their own. If such a strongly magnetized star collapses, the simple crushing of its already strong field, concentrated by the collapse, might reach magnetar strength without any dynamo at all. The field would be a fossil, a relic of the star that died. So there are two pictures. In one, the magnetar's field is made in the moment of birth by a furious dynamo, and the key is how fast the newborn core was spinning. In the other, the field is an heirloom, passed down from a parent star that was already strongly magnetized, and the key is the magnetism the star carried in life. Both can reach the right field strength on paper. Telling which actually happens, or whether both do for different magnetars, is an active question. There are more open puzzles. We do not fully understand the giant flares, the precise way a global rearrangement of the field unleashes so much energy so fast. We do not fully understand how magnetars produce the radio flashes that link them to fast radio bursts, or why some magnetars make them and others seem not to. We do not know the true size of the hidden population of old, quiet magnetars, only that it is probably large. Each of these is a real gap. There is also the matter of the strange neutron stars that blur the categories. Astronomers have found objects that seem to sit between magnetars and ordinary pulsars, neutron stars with fields in between, or with some magnetar-like behaviour but not all of it. The clean division between a pulsar and a magnetar may be less a sharp line than a spectrum, with objects scattered along it. Where exactly the boundaries fall, and what sets an object's place on that spectrum is not fully settled. None of this should trouble us. It is how a living science looks. The core of the Magnetar story is solid and well tested. We know these objects exist. We have measured their fields. We understand in outline how they form and behave and die. The open questions sit at the edges of that solid core, at the frontier where the work is still being done. A magnetar is so extreme that it pushes our physics to places we cannot easily check, and the questions it raises are exactly the questions worth asking. That is where the science stands, partly known and partly open, which is the truest place any real story can rest. We have built the whole idea, from the magnet on your fridge to the engines that may power the brightest explosions in the universe. It is time to return to where we began, to that small magnet holding a photograph, and answer, in the plainest words, the question we started with. Go back to the magnet on your fridge. It is still there, holding up the photograph, gripping the steel through a sheet of paper, weak enough to pull free with 2 fingers. Nothing about it has changed, but you can see it differently now, because you know what stands at the far end of the ladder it sits on. That small click of force in your hand is the same force that, pushed to its limit, remakes matter and lights up galaxies. We began with a simple question. How strong can a magnet get? Now we can answer it plainly. A magnet can get strong enough to be a star. At 1,000 trillion gauss, the field of a magnetar is 10 trillion times stronger than the one on your fridge, strong enough to crush atoms into needles, to give empty space a grain that bends light, to outweigh lead with nothing but stored energy, and to kill from 1,000 kilometers away by unmaking the molecules of anything that nears it. That is the answer to the title. That is how strong a magnet can get, and that is why nothing survives close to one. And we can say what a magnetar really is, in the simplest terms. It is the corpse of a giant star, crushed in a supernova into a ball of neutrons the size of a city, carrying the strongest magnetic field in the known universe, frozen into it at birth. It spins, it strains, its crust cracks, and it speaks to us across the galaxy in flashes of gamma rays and radio. For about 10,000 years it rages, and then it falls quiet, joining the dark and silent crowd of dead stars that fills the Milky Way. Hold the 2 pictures together, the fridge magnet and the magnetar, and feel the distance between them. They are the same force, the same magnetism, the same physics that turns a compass needle. The only difference is how far it has been pushed. The universe took the gentle pull you know from your kitchen, and, in the death of a great star, concentrated it until it became one of the most extreme things that exists. There is no new force out there. There is only the familiar one, carried to an unimaginable degree. That is the quiet lesson these objects offer. The cosmos is not built from forces alien to us. It is built from the same handful of forces we meet in everyday life. Gravity that drops a cup, magnetism that holds a photograph, the same rules running everywhere, from the kitchen to the heart of a dead star. What changes is the scale, the density, the degree. Learn the force in your hand well enough, and you hold the thread that leads all the way out to a magnetar. There is something steadying in that. The magnetar is strange, almost beyond belief, a place where matter and space and chemistry all bend. But it is not beyond understanding. We reached it step by step from a fridge magnet without ever leaving the solid ground of real physics. The universe at its most extreme still answers to ideas a patient person can follow, one simple step after another, late at night, from something familiar. So the next time you pass your refrigerator and see that small magnet doing its quiet work, you might pause for just a moment. In your hand is the gentle end of a force whose other end, out in the dark of the galaxy, holds dead stars in a grip strong enough to break atoms. The same thread runs through both. You live in a universe where that is true, and where a curious mind, starting from a photograph held to a fridge, can come to understand the strongest magnets that exist. That is worth knowing. And it was there on your kitchen door the whole time,